One of the best ways to learn new ideas and new ways of thinking is to master the vocabulary words of the idea. In this video, we're going to go over some of the big vocabulary words of engineering systems analysis: design variables, parameters, objective functions, and constraints. I'm going to talk about each one of these and give some examples so that students will learn what they mean and be able to improve their reading, discussion, and mastery of engineering systems analysis. Let's start with the design variables, because these are the choices available to the engineer. These are the things that constitute the design. They are the independent variable or variables that engineers get to choose. There are some good examples of things that engineers typically get to choose. One of them might be the materials that make up a design. That could be wood, metal, glass, plastic. Another one are the dimensions. It could be volumetric dimensions. It could be alignment, for example, of a highway route or a canal or a railroad track or something in civil engineering. And sometimes this is fairly common. There are a lot of time or schedule or resource allocation problems in civil engineering, in engineering systems. So these are some of the examples of the choices that engineers make that constitute a design. They might also come in the form of what I call a discrete choice. That is, rather than a continuum of dimensions or a continuum of time, we have to make a choice between two different packages. For example, we might choose an Android or an iPhone. In this case, the choices are mutually exclusive, although they do pretty much the same thing. They both might satisfy the requirements. They represent a package of different choices that are two discrete alternatives. So now we have an idea that the design variables are those independent variables. Typically the independent variables are the ones on the horizontal axis or the x-axis that the engineer must select from a range of alternatives. And that could be a continuous range, for example, like in a dimension, or it could be a discrete choice, like in wood or metal or plastic, or a discrete alternative in the sense of a total package of technology, or it could be a resource allocation problem like time, schedule. Those design variables must be chosen within the operative constraints. So suppose that we choose a matrix or an array of design variables. It could be multi-dimensional. We could have lots of different indexes. In this case, I'd said a three-dimensional matrix. Each one of these design variables is likely subject to some constraint. Whichever the design variable is, there might be a maximum and a minimum constraint into which the design variable must ascribe. That is, it has to fit either within these physical dimensions, or it has to fit within the start and finish time, or it has to fit within whatever the constraints that bound the feasible region on the design variables is. So what's a feasible region? It's the combination of design variables, any combination that satisfies all of the constraint equations. In this case, I've shown two inequality constraints. There could be some combination of design variables. Let's say any example will do that equal some constraint. And in this case, could be inequality or it could be an inequality, but when we combine design variables like this and write a constraint, typically that's a balance constraint. For example, a mass balance is a special kind of balance constraint. We might have an intersection, cars going in and out, and one of the rules of the intersection, the way we model, is that all the cars go in have to come out. There's no parking inside the intersection. So that's a special kind of mass balance, which represents a combination of design variables that have to equal or it could be an inequality related to some constraint. We could also have these inequality constraints that work on one or more design variables, but there's no such thing as an equality constraint for a single design variable, because then the engineer has no choices available. The constraints put limits on the choices that are available, but within those limits we find the feasible region, that is the combination of design variables that would satisfy all the constraints. There are some parameters in every systems model, and the parameters are things outside the engineer's control, but they don't directly bound the design variables. So what could that be? It might be things like physical constants. You don't get to decide the acceleration of gravity, you just have to live with it. But more common are things like prices or costs. These are outside the engineer's control, but they certainly work into the design model. They just don't put a bound, not a direct bound perhaps, on the feasible region. It could also be something like weather. We don't yet get to control the weather. We have to accept the weather as part of our model, even if it does not directly act as a constraint. It may have an impact upon our design. One of the reasons that we are interested in these parameters is because we often want to do a sensitivity analysis to see what happens with different aspects of the design as we change a parameter. As prices go up, maybe some choices become more attractive and other choices become less attractive. Perhaps interest rates change and our evaluation of design alternatives change. So it's important to keep track of these parameters, even though they're outside our control, in ways that we can test the sensitivity of our models relative to these parameters. Finally, the objective function or the merit function is one of the most important vocabulary words. Why is that? Because of all the feasible solutions represented by all these different combinations of design variables that satisfy the constraints, of all the feasible solutions, the mathematical representation of their merit or their value, I'll call that C, which is a function of the design variables and the parameters. This mathematical representation is how we decide, is how we judge, is how we assess whether one combination of design variables is superior to the other. This is why it's sometimes called a merit function. How do we know whether one feasible design is better than all the rest? We have to compute the mathematical value of the objective function. And every systems optimization problem is either going to be to minimize that objective function or maximize it. The word objective can be confusing because sometimes students will think, well, that's our goal. But objective is not a goal, because objective is going to be either a minimization statement or a maximization statement, and it's going to be formally represented in a measurable objective function. And here's something else that's important. You only get to do one objective function at a time. You don't get to simultaneously minimize one thing and maximize another. You either take them in order. You minimize your first objective, and then accepting that as a constraint, you might maximize the second objective so long as it doesn't damage the value that you got for the first objective. You can take different objectives in order, but you have to do them one at a time, or combine multiple objective functions with some sort of averaging or weighting function into a single function. It's very important to recognize that objective functions in systems analysis will be mathematically expressed, and they will be accompanied by minimization or maximization principles. The objective function is the way you measure or assess whether one design is superior to any other. So let's take a simple example that illustrates some of these. We said the design function is going to be the independent variable, and we typically draw the independent variable on the x-axis. So this is some choice that we make, and we might call this retention time. Retention time could be measured in hours or minutes, but we're going to design a tank, and the tank is going to contain a chemical reaction, and that reaction has a certain kinetic aspect to it so that it proceeds in time. And then over here we're going to have cost. This is our objective. We have a single design variable, retention time, and the design variable of retention time is dependent upon something like the volume of the tank over the flow through the tank. There's lots of different ways that this could physically wind up represented, but for right now our design variable is retention time and z is our cost. Perhaps as retention time goes up, so cost has some sort of a function. It might go up at first. If the tank gets bigger, maybe it comes down later. We don't know the dynamics of this particular reactor or this unit within the overall system, so we've just postulated some sort of a curve like this. If it were our goal to maximize cost, we would find this right here. But it's not our goal to maximize cost. Typically, it's our goal to minimize cost. I've only plotted so far this cost curve for the retention times that satisfy the constraints. So this is one constraint, T min, and here's another constraint, T max. I don't know why these are constraints, but I do know that our design variable T must be greater than or equal to T min and less than or equal to T max. Where does that leave us? Remember that we're asking for the minimum cost, and we have 2 points that suggest themselves. Both of them are extreme points. The extreme points are found where the design variable will satisfy a constraint equation. Even if it's written as an inequality, we'll satisfy it as an equality. And the only way to solve this nonlinear problem, the way it's represented here, is to test these 2 extreme points and discover which one of them is least cost. Of course, we can see graphically that the least cost shows up right here. And that means that in this example, T equals T max is the active constraint. An active constraint is when the solution is found in a way that satisfies this constraint equation as an equality. What that means is if for some reason the active constraint were to slide, the solution would have to slide too. The feasible reason in this one design variable problem is found between T min and T max, and the solution is found at T max as an active constraint. That means that T min is an inactive constraint. And this vocabulary becomes important so that we understand how to explore the problem and which constraints the problem is sensitive to and which it isn't. Problems will only break along the active constraints because we could move an inactive constraint and the solution won't change. So now we have a rudimentary nonlinear example that helps us understand the meaning of the objective function. In this case, the objective function is that mathematical representation that shows whether we prefer one or another combination of design variables. We understand the meaning of design variable. It's that independent variable or set of independent variables that the engineer gets to choose in such a way that will maximize or minimize the objective function. We understand constraints. Constraints are those values that bound the choice of design variables. But I didn't explain very well parameters. Parameters wind up embedded somewhere in this curve that I glossed over because we don't really know what the aspects of the kinetics of this reaction are. In this case, the parameters could be things like the reaction constants that govern whatever this conversion process is. These are the physical parameters that we can't control, but of course our problem is sensitive to them and we have to include them in our model. This gives us an example of the 4 key vocabulary words of systems analysis and some of the other words that are going to be important to keep in mind as we learn how to formulate systems optimization problems.